Welcome to lecture number 11 for ECE 321 Analog Electronics. Today's lecture we talk about analog computers. Now, an analog computer is an electric circuit that implements a differential equation. In my book, if you can't play Star Trek on it, it's not a computer. Well, with analog computers, you can't play Star Trek, but they're still considered computers. They solve differential equations. What analog computers do is they allow you to duplicate the dynamics of an expensive system using an inexpensive circuit. And analog computers have been around for quite a while. For example, here's a picture from 1949. This is an analog computer. What you've got, all these knobs are potentiometers. You can sit there and adjust the knob and adjust the resistance. There are also capacitors in there for integrators and some oscilloscopes. So this is what an analog computer looked like back in 1949. With this, I could simulate the dynamics of a system, like a rocket. The application of analog computers, they've actually been around for quite a while. For one example, I used to work at GE aircraft engines, and in the test cell, if you want to test a jet engine, it costs $10,000 a minute to test a jet engine. If you screw up and the engine goes unstable, you just blew a $4 million engine. From an input-output standpoint, the jet engine satisfies the differential equation. If I build a circuit that satisfies the same differential equation, input-output is the same. The nice thing about a circuit is it costs 10 cents a kilowatt hour to operate. If it goes unstable, a red light turns on. If something really bad happens, you blow a capacitor. Much cheaper, much easier to work with an analog computer. Plus, you can build a bunch of these, wire them up, and have 10 test cells rather than just one. So again, this is what the analog computers look like in the 1960s and 1970s. This would be basically a circuit. On it, you've got a bunch of different resistors, capacitors. You can sit there and connect them together with these wires. And if you wire it right, it'll look like a jet engine. This is actually what NASA used to have. NASA had a test engine that people could design feedback controllers for, and you'd go out to NASA Langley to test it. Before you could touch their engine, you had to prove your controller worked on an analog computer. If it didn't work on the analog computer, they wouldn't let you anywhere near their engine. The analog computer was wired up to have the same differential equation as the jet engine. So from input-output standpoint, you didn't really care. Was the thing connecting them an op-amp circuit? Was it a real engine? As long as it satisfies the same differential equation, it behaves the same. But this is much cheaper to operate, and if you mess up, it's not nearly as expensive. Once you proved your design on the analog computer, you would then run it on the test cell. You might be allowed to run it on the test cell. Now, to come up with how to implement a differential equation using an analog computer, let's go through an example. So here, suppose I want to implement the following nth order differential equation. I've got n zeros, n minus 1 zeros, n poles. Find a way to do that. And there's many ways to do it. Here we're going to go through one approach. And just to give us something more manageable, let's assume I have a generic third order system. The first step is cross multiply. Well, actually, the first step is to create a dummy variable called x. Let's have x be 1 over the denominator. And then y will be the numerator times x. The second step is come up with a way to implement x in terms of u. To do that, I cross multiply, take the denominator and multiply on the left. Solve for the highest derivative, gives you s cubed x, and bring everything else right, so I get a sign change times the other terms and the input. Third step. Once I've got the third derivative of x, so this is the third derivative using prime notation. If I integrate once, I get x double prime. Integrate twice, I get x prime. Third time, I get x. Set up 3 integrators to generate x double prime, x prime, and x. And in theory, I could go the other way around. Given x, I can take the derivatives and give you x prime, x double prime, x triple prime. I don't do that because noise gets amplified by differentiators. Yeah, typically signals will look like this. If I integrate it, that cleans up noise. If I differentiate it, I'm going to get fuzz. So differentiators are just terrific noise amplifiers. That's why I avoid differentiation. Instead, I like integrators. Integrators clean up signals. If I have high frequency noise, the high frequency gain is 1 over s. As s goes to infinity, the gain goes to 0. So that's why we use integrators. But anyway, back to the ranch. I have the third derivative. Integrate 3 times, I get x double prime, x and 1. Fourth step. This is my transfer function. I can create x triple prime by adding up the input u minus a2 times the second derivative of x minus a1 times the first derivative of x minus a0 times x. So this implements the transfer function from u to x. Next step. Now that I know x, x prime, and x double prime, I can do the numerator polynomial. I can determine y in terms of x, x prime, and x double prime. So this implements my transfer function, and the nice thing about this approach is I had let's see, you had your b2s squared. It looks like I need to take the second derivative of u. I don't. I really don't want to take the derivative because derivatives tend to amplify noise. This avoids differentiation, and kind of what you're doing is that I could do right here b2 times the second derivative of x. But if I go back, here's the first derivative of x, here's the second derivative of x. I can clear out the s squared just by feeding back this signal. So I don't need to use any derivatives when I implement the filter. Next, I need to build the circuit. Now the circuits that we're going to be using is to build an inverting amplifier. I've got this circuit. So here's your minus, plus. This circuit has a gain of minus R1 over R2. If I put 2 resistors in, I have a summing amplifier. The gain is RA, that's an A, RB, is minus R1 over RA times A, minus R1 over RB times B. So I can build a summing inverting amplifier with this circuit. But the gain's always negative. So I'm going to start using this notation. A triangle with minus signs at the input, the gains. This is the gain times A, gain times B, and I want the gains to be negative just because the circuit I'm eventually going to be using has a negative gain. If I need an integrator, it'll be the same circuit. Yeah, 2 inputs. But instead the feedback is a capacitor. This is an integrator. The gain is, let's see, RA, RB. The gain for this one is minus 1 over RAC times A times integral of A minus 1 over RBC integral of B. So this will be an integrator. That's an amplifier. So to implement my circuit, I'm going to change my notation. Instead of using integrators and summing blocks, I'll use this block. That means an amplifier. I'll use this block. That means an integrator plus a summing amplifier. And the reason I'm doing that is the last step, I can implement it. This block goes to an integrator. This block goes to an amplifier. I can now build it. So, switching over to analog computer notation. I had 3 integrators. So here's one integrator. There's the second, there's the third. I had 3 feedbacks. This gain went times minus A2x. This was minus A1x minus A0x. And the output was plus B0 times x plus B1 times x prime plus B2 times x double prime. So this is the same as this block diagram, just using different notation. This is using analog computer notation. Now, problem with this is I need negative gains. When I implement it, all the amplifiers I'm using have negative gains. These have plus gains and minus gains. That's a problem. So what I'm going to do is change all the gains to be negative, and I need to make sure I don't get any sign errors. So the gain around this loop needs to be negative. The gain around this loop needs to be negative. Gain around this loop needs to be negative. Plus the gain from U to each of the outputs needs to be positive. So let's do that. Let's make all these gains negative. Do minus, 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 then check. Here the gain is negative, that's okay. Here the gain is minus, plus. I have two negatives, gives me a plus gain. I need another negative, so I'll throw in a minus sign right here. Gives me a triple negative. Essentially I need an odd number of op amps around each of these loops. Around this loop I've got 1, 2, 3, triple negative, that's okay. For the input, here's 1, 2 inversions, gives you double negative, that's positive. 1, 2, 3. I've got a sign error, so let's throw an inverter in right here. And 1, 2, 3, 4, positive. So I'm going to be throwing in the minus signs. Occasionally I might have to throw in an inverter, just to give me another minus sign to keep the signs correct. So this is an analog computer where all the gains are negative. I like that because this I can implement. And to implement it, so here's your integrator. I've got 4 inputs. So here's 1, here's the second, third, fourth. For U, 1 over RC is 1. For here, 1 over RC is A0. 1 over RC is A1. 1 over RC is A2. This has a gain of 1. This has a gain of 1. Gain of 1. This has a gain of B0. 1 over B0. This has a gain of B1. Gain of B2. So this will implement it. And one trick that's done is I could use my standard being 1 ohm, 1 farad. The problem is that 1 ohm uses too much current. 1 farad is a really big capacitor. What really matters is that I keep 1 over RC the same. I could make R 10 times bigger and C 10 times smaller. Or I could make R a million times bigger. So my units of R 1 mega ohm and 1 microfarad. So in this circuit, 1 means 1 meg. 1 means 1 farad. So all these guys are in terms of mega ohms and microfarads. And there's your circuit. That's a generic third order differential equation. It needs quite a few op amps. What is that? 4, 5, 6. 6 op amps to implement a third order differential equation. What we did before is with a Butterworth filter, I was able to build a third order Butterworth filter with just 1 op amp. That's a different circuit. Kind of uses a different approach than analog computers. It's another way of doing it. This is one where I take the differential equation, implement it using integrators, feedback to place the poles, take the outputs to generate Y. Another way of doing it. As a sidelight, this technique works well if all the poles are close to 1. If the poles are not close to 1, you start getting really large numbers. So typically what's done is you change the time scaling so that all the poles are close to 1. Again, T is not a universal constant. If I have the settling time, if the pole is at -1, it decays as e to the minus t. The settling time is roughly 4 over the pole, about 4 seconds settling time. If my pole is at -1000, that decays as e to the minus 1000 t. The settling time is 4 milliseconds. If I change my time scale so that 1 unit of time is 1 millisecond instead of seconds, then the pole becomes 1, and the values become much easier to analyze. I can then change time. These are integrators. If I make C 10 times smaller, I integrate 10 times faster. Again, for an integrator, the gain is 1 over c integral of I dt. If c is 10 times smaller, I integrate 10 times quicker. I respond to frequencies 10 times higher. I basically kept the poles exactly the same, just time is now scaled to be 10 times faster. So I can do that, design for 1, change all the capacitors to be 0.1 microfarad, I now run 100 times faster. Change them to be 0.01 microfarad, it runs 100 times faster. Or I can make it slower as well. 10 microfarads makes it 10 times slower, 100 microfarads makes it 100 times slower. That's easy to do. And this is a way that when you do simulations, I don't have to simulate in real time. For examples, as the Fed changes the interest rates or the money supply, the economy speeds up or slows down, but that happens in the order of months, not years. If I were to simulate the US economy, it satisfies the differential equation, I could build it with this circuit. I don't have to run it in real time so that it takes 5 months to respond. I could have it respond in 5 seconds. Just change the capacitors so that 1 month becomes 1 second, and I can see what's going to happen much quicker. Or if you have something that's really, really quick and I want to slow it down, say something that happens in 4 milliseconds, I could slow it down so that 1 millisecond real time is 1 second real time. Have it run 1,000 times slower. So these step responses that look like this, that happen in 4 milliseconds, now happen in 4 seconds, and I can see it. That's one trick you can also do with analog computers. I don't have to simulate in real time. I can speed it up, I can slow it down, and to do that, you just scale the capacitors. Currently, analog computers are no longer used like this. This is from the 1950s through 1970s. The problem with them is you have all these wires. It's hard to debug. If a wire falls out, it gets put in the wrong spot, hard to debug. It's hard to make copies. If somebody says, hey, I really like that, can I get a copy? Well, maybe. Plus they're expensive, a couple $1,000, maybe $10,000 for this. In terms of mathematics, anything that satisfies the same differential equation behaves the same. Now with MATLAB, I can do the same thing on a computer. And there are graphical languages like LabVIEW, Simulink, VisSim that let you implement differential equations using drag and drop. And it really just runs a MATLAB script that solves differential equations, implementing your block diagrams. So these guys, typically the way you input the system is like this. I can draw integrators, semi-junctions, connect them up. I can actually just do a whole transfer function as one block. That's VisSim, Simulink, Circuit Lab. That's actually how these are worked or implemented nowadays. Plus, a lot of these functions, they have an analog input, analog output, so you can take your computer, connect it to an analog input, have it drive the system, it feeds into Simulink, calculates the voltages, spits that data to a D to A converter, and from an input-output standpoint, I have an input, I have an output. In between, it satisfies the differential equation. I don't really know or care. Is it the real system? Is it an analog computer? Is it a Simulink program? Really makes no difference to me. But this is actually much easier. Plus the advantage is that anybody with a computer with Simulink installed and analog input, analog output, I can run the same simulation. And that's much easier, much easier to share than the analog computers or the physical system. So that's how things are done today. So to give an idea what VisSim looks like, VisSim is very similar to Simulink, very similar to LabVIEW. I like VisSim, but they're all really about the same. If I want to implement a differential equation, I've got these things like blocks. I can bring in an integrator. VisSim is actually really easy to use. There is an instruction manual. I've never looked at it. I haven't really needed to. If you're looking for something like a summing junction, it's kind of go through here and keep going until you find it. If I want to add gains, like block arithmetic, here's a gain. if I highlight it, I can flip horizontal. This is really just for cosmetics. Arithmetic, gain, edit, flip horizontal, edit, add connector. So I can add these in like so. There goes the first integrator, second integrator. So it's really nice. It's just a drag and draw package. So maybe let's call this -2. This -10. The input is a signal producer. Let's do a step input right here. And I want to look at the step response. This is the one that's kind of odd. This is a signal consumer, is a plot. And I don't like the default colors, so I'm going to change the appearance of the background to white. So now I can run it. So here's the solution to that differential equation. If I go under simulation, I can change it. I want to run for 5 seconds, step size 0.001. I can change the integration method, pick your favorite form of integration. I've got Euler, trapezoid, Runge-Kutta, second order, so on. Pretty much the further down the list, the better. I like fourth order Runge-Kutta. Take the step response. That's one approach. I can also, under linear system, input the system just like this. And this would be, say, 1, 2, 3, 4. There's the numerator polynomial, denominator polynomial. What's that step response? And that was probably unstable, but it is another way to input a system. With BISIM, Simulink, LabVIEW, under blocks, they usually also have a way to input analog signals, output to the data A. I've got time delays, noise generators, stuff like that. And the producer, random generator. Here we go. If I have noise, kind of mentioned that differentiators amplify noise, integrators clean it up. So let's get rid of this. If I have a noise input and I integrate it, block, integration, integrator, so this is zero mean, standard deviation 1 noise. The red line is the noise. The blue line is when I integrate it, it really cleaned it up. It was going plus or minus 2 about. It's now, just a random walk, about 0.1. That's an integrator. A differentiator, you can't actually implement in these languages. But what I can do is I can approximate it. If I have 10s over s plus 10, the way you input this is decreasing powers of s. So there's 10s over s plus 10. And I'll tell you what it thinks it is. At low frequencies, this is roughly 10s over 10, a differentiator. This is a noise amplifier. It went from plus minus 1 to plus minus 20. That's why we dislike differentiators. And another neat thing, if we go under discrete, here's my sampling rate. It treats this as powers of z. So here's my digital filter, 10z over z plus 10, which is unstable. Let's do z over z minus 0.9. That's a digital filter. If I give it a sine wave input, producer, sinusoid, change the sampling rate, we get stair steps, and you can see the sampling rate. So that's BizSim. That's really how analog computers are implemented today. So in summary, analog computers are just op-amps. They allow you to implement any differential equation. The heart of an analog computer is the inverting integrating circuit. That's this guy right here. Input's a resistor. Feedback is a capacitor. And it's a negative inverting amplifier. Plus you add in inverting amplifiers and summing junctions, and you can implement any differential equation. These are somewhat dated. Again, you can do the same thing with a microcontroller using BizSim, Simulink, LabVIEW. But sometimes analog computers are sufficient. Like I don't necessarily have to have an entire computer to implement a PI controller. Say for toaster, I don't want to have Windows 10 computer running my toaster. I can do the same thing with an op-amp, 2 resistors and a capacitor. So sometimes analog computers make sense. Sometimes, if it gets really complicated, I'd rather use a microprocessor. So it's a tool. If the tool helps, use it. If it doesn't help, don't use it. So that's analog computers and lecture number 11 for ECE 321.